Hi. All right, so you're going to get to see me tonight. So I wanted to give you a demonstration for my B-Day kids that aren't going to see me tomorrow because I'm out of my beautifully precisionally cut function machine. Go with it, guys. Go with it. So basically, let's talk about what the word function means. Function means a job. What does something do? So like, for example, my function is to teach. So I know you learned about input-output tables last year, X, Y, independent, dependent variables. But let's take me, for example. So into my function machine, we put me, and then there was a whole lot of college and training and teaching certificates, and my output was hopefully a good teacher. So using that example, I want to bring that to math a bit. So for example, this function machine's job is X plus 3. Go with it. So what that means is I'm going to input a number. I'm going to input an X value. So an X value goes into my function machine. X plus 3 is applied to that, and what do you think will come out? If a 3 goes in, meaning the 3 gets put in place of X, out comes, wait for it, a 6. That's my Y value. So this would be an ordered pair for this function. This is backwards. Let's see if I can figure out how to do this backwards. Okay, so this is my X. Try to figure out how to do this backwards. This is my Y. What happens is I put a 3 into my function machine, meaning that that took the place of that, and out came a 6, because 3 plus 3 is 6. Okay, let's do some more. 2. That is my X value. That is my input value. So I put in a 2 into my function machine. What do you think is going to pop out? So meaning a 2 is going to go right here. 2 plus 3 is 5. So there we go. That is our Y value. That is our output. Let's try this one. We could put in a negative number. So I put in a negative number into my machine, meaning it takes the place of my X. So it goes into my machine. And what do you think will come out? What is negative 3 plus 3? 0. So that would be an ordered pair. So I could graph. I should have rehearsed this. Nope. X, Y. This is laughable. This would be my ordered pair. And I could graph an ordered pair. Okay. So, but now I'm going to have my machine do a different job. My machine is now going to do something different. But what I want to explain to you is that this is the additive relationship. So we're not going to have a subtractive relationship. We're going to have an additive relationship. So how do I know this is an additive relationship? I should not record these at midnight. It's because, well, we have a plus sign. Whereas this would be what we call a multiplicative relationship. And we'll talk about it. But we don't have a divisive relationship. We have a multiplicative relationship. And I'll go into more detail about that in a second on my slides. So, if I put in, let's say I put in a 10. This is my input. This is my X value. This 10 is going to go in place of my X. So that would be 3 times 10. So if I put in a 10, 10 times 3 is what? 30. So that would be my output variable. Let's see. 4. So if I put in my 4, 4 is going to take the place of my X. So it will go right here. 3 times 4. I put a 4 into my function machine, and out pops a 12. Okay, so we're starting to get the hang of this. The job of a function is to take your X value, apply to it whatever your function or your expression is telling you to do, and then get your output variable, aka your y. Okay, last one. So yes, I can do a fraction. So that would just be 3 times 1/2. So I put a 1/2 into my function machine, meaning it will go 3 times 1/2. What is 3 times 1/2? It's not 3. 1/2 plus 1/2 plus 1/2 is 1.5. So that would be my value, my output value. So that's just a little demonstration I wanted to show you as far as what a function is. Okay, so now I want to kind of continue talking about how a function looks in written form instead of a big old box with orange pieces of paper. So the big thing to notice is that we have 4 different input-output tables. These are 4 different situations. They're going to have 4 different functions. But how do we decide which one is which versus this is an additive, where a is our constant, and this is our multiplicative, again, where a is our constant. Oh no, Manny's ball is rolling under the table. I don't have time to get it right now, dude. You're going to have to hang on. Okay, so what's going on between this 14 to 27? So, well, the whole point is to try and find patterns. So 14, is it 14 times something equals 27? Meaning I put a 14 for my x, I times it times my constant, and I get out a 27. Yeah, I could do that, but that would be a super complicated decimal, which I don't want to get into. But let's see if there's an easier way. What's the difference between 14 and 27? AKA, we are adding 13. So, that would mean, Manny, y equals x plus 13. Okay, so let's see if that applies to the next one. 72 plus 13 equals 85, so that works as well. 35 plus 13 equals 48, meaning I put a 35 in here, I add a 13, and my function spits out a 48. I put in a 78, add a 13, get a 91, so all these work. And the important thing to see here is if I wanted to plot this on a graph, that's just an ordered pair. This is your x column, all these are x's, all these are y's. So, if I wanted to plot that on a graph, that would be 14, 27. That would be 72, 85. You get the drift. Okay, hang on. Let me get the ball. Okay, the ball is back in the mouth. So, something interesting will be y equals x plus 13. Okay, so let's look at this next one. Oh, interesting. I'm going down. So a lot of people will be very tempted to say, oh, that is y equals x plus, is y equals x minus 4. But this is an additive relationship. We don't have a subtractive relationship that we're talking about. So what's another way that I can lose 4 but still have a plus sign? I can add a negative 4, or adding a debt of 4. So if I put in a 62 right here into my function, and then I'm adding a negative 4, which you could say is just subtracting 4, my output, my y, is going to be 58. So again, this is an x, y, ordered pair. Okay, so next, 92. If I put a 92 right here, and I add a negative 4, I will in fact get an 88. Same thing with 102 to 98, 66, 62, 38, 34. Okay, so that is just 2 examples of input-output tables for additive relationships. Now let's talk about multiplicative relationships. So you could say, well, wait, looking at this first ordered pair, this is y equals x plus 4. Because you put in a 2, you get out a 6. But going to the next one, let's see if that applies. If I put in a 10 and I add 4, I would get a 14, and it's 30. So this can't be my function for this one. So what else is happening? I'm putting in a 2 and I'm getting out a 6. So what about this? Would that work? 2 times 3 is 6. 10 times 3 is 30. 12 times 3 is 36. It works. And remember, when we have a number next to a variable, we don't have to put in a dot right there. That implies multiplication. Okay, so I have a multiplicative relationship, and these are my ordered pairs. So if I were to plot this on a graph, which I'll do a couple more in a minute, my x would go at the bottom, my y would go up and down, and I would go, this was 2, and then this was 6 up here. I would go over 2, up 6, and put my dot. Okay? All right, next one. So this one's kind of tricky because just looking at the first one, I would say, oh, well, this is y equals x plus a negative 27. Let's see if that works for the next ordered pair. Put in a 40 right here, add a negative 27. Well, that would give me a 13, and that's definitely not 13. So this is not an additive relationship. So it has to be a multiplicative relationship. But what on earth do I multiply by and get a smaller number? This isn't a divisive relationship. This is multiplicative. What about a decimal? So what about a decimal less than 1? If I multiply 30 by something less than 1, don't you think I'm going to get something less than 30? I will. So this is going to be a 0.1x. That is my function. So Ms. Smith, how on earth did you get that? Well, let's see what happened to get my 30 to 3. You're like, no, you divided by 10. Interesting. You're saying I divided by 10. Dividing by 10 is the same as multiplying by 0.1. Okay, so 40 times 0.1. So let's look at this. So you're saying, let's go back to the 30. So I could write a 3. So yeah, 30 divided by 3 equals 10. I see your point. But what is 30 times 0.1? 1 times 0 is 0. 1 times 3 is 3. We have one decimal to consider. 3. So that's why those are equal. So these are just 4 examples of adding a positive, adding a negative, multiplying by a number greater than 1, and multiplying by a number less than 1. Okay, so moving on, let's look at some examples. So, and these are all different ways to describe our relationship. We can use an equation, we could use a description, a graph, or a table. And what I mean by table is an XY table. So in this case, it just gives us a description. So the industrial tech teacher told his class to add 2 inches to the length of each student's project. So, trying to decide if this is an additive or multiplicative relationship. I don't know. The adding 2 inches, that kind of tells me that however long the student's project is, I'm going to add 2 inches to that. So if I start off with a, let's see, a 1-inch project, I put in a 1 for right here. Put it in my machine. It gets added by 2 and out shoots a 3. So if I wanted to graph that, I would go 1 to 3, something about there. Okay, this is nothing more than an ordered pair. Okay, so what if I have a 2-inch long project? Put it in for x, add 2, shoot out a 4. Okay, we can keep going and going. Put in a 3, I will get a 5, graph that. Put in a 4. For my x, add 2, I will get a 6. And put in a 5. Right here, add a 2, I will get out a 7. Okay. So that is what it graphed. The next thing I want to talk about is the whole idea of an independent versus a dependent relationship. So we have learned, but I want to remind you, that your x variable is always the one that goes across the bottom. X looks like a sideways cross. That's how I remember it. X across. So if x is going across, then y is the one going up and down. Okay? So also remember that x is your input, which would make your y an output. Okay. So now let's talk about the difference between a dependent and an independent variable and which one goes where. So your x, your variable that goes across the bottom, is going to be your independent. I remember it, I for input, I for independent, which would make your y your dependent. And we'll talk about why. Because this depends on what you're starting with. I'm going to say that again. Your 3 depends on your 1. You're not going to get a 3 as your y value. That's Manny drinking his water. Yay! Say hi, Manny. Oh, more. So we're not going to get a 3 unless we input a 1. So you could say our y depends on what our x is. Manny! It's like a camel. So I input a 1, I get out a 3. So the 3 depends on the 1 being there. Okay. Here's an example where they give us the equation. Oh, Manny, the sound effects. They're beautiful. And I could come up with a description and a graph. So if I wanted to just start picking points, meaning I put in a 0 here, I'm going to get obviously a 10. If I put in a 1, I'm going to get an 11. I put in a 2, I'm going to get a 12. You see the point. Okay, so if I wanted to graph that, well, first I would put my x down here, because x always goes across, my y there, and I could make this as my 0, my 1, 2, 3, 4, 5. I'll start here at 5, 6, 7, 8, 9, 10, 11, 12, 13. I want you all to come and try and write with this thing. Okay, so 0 would be 10. 1 would be 11. 2 would be 12. 3 would be 13. 4 would be 14. So forth. Okay, and a description. So now I could come up with a description to describe this equation. It could be something super simple like, if I put $0 in my bank account that has a balance of $10, 0 plus 10 would be 10. If I put in $1 to my bank account that already has $10, I will then have $11. So I'm not going to write all that out, but that's just an easy description for that. Okay, so this one, I'm just given a graph, my friends. So just from my graph, I can build up all of these things. So if I put in, if I start with 50 as my x, what's my y? Remember, my y is going up and down, so my y is 0. Interesting. Okay, so let's look at 75, because halfway between 50 and 100 is 75. So if I put in 75, or if that's my x value, then my output will be 25. So what's happening here? So at 100, because I go out to 100, this is my x, this is my y. If I have 100, I'm going to end up with $50. So my equation for this, yes, it's additive, but it could be x plus a negative 50. So this could be something like playing a slot machine. You put in $50, you end up with $0. You put in $75, you still lose $50, but then you'll have $25 left over. You put in $100, you still lose $50. You have $50 left over. So that's that type of thing. But what I want to reiterate is that this is your independent variable. You're going to get a break after this, I promise. And this is your dependent. Because it depends on how much you start with to tell you what your y value will be. It depends how much you start with your x variable to what your y value will be. Technicians carry a 15-pound tool belt. Which equation best represents the relationship in the table? So this would be your XY table. So your x is here, your y is here. So the top is always going to be your x. So this is going to be, I'll just put tech. And here I'll put total. Pretend that's a straight line. Okay, so if your technician weighs 130 pounds, once they put on their tool belt, what is their total weight going to be? So it tells us, well, their total weight's going to be 145. So I'm seeing an increase of 15. So let's look at the next ordered pair. If my technician weighs 150 pounds, once they put on their tool belt, they will weigh 165 pounds. So I am seeing an increase of 15. So I can cross this one off and cross this one off because it's not multiplicative. It is additive. Okay, so now I got to figure out which one's which. So that depends on what the question's asking. So W is my total weight. So W is my output. It's my Y value. So because of that, I can cross that one off. Because W equals T, weight of your technician, plus 15 pounds. That will give you W. Okay, so C is the right answer for that one. Okay, Miss Postenbach, go ahead and give them a 3-minute brain break. For 3 minutes, they can relax. But in 3 minutes, they need to come back. Okay, guys, brain break over. For those of you watching at home, hope you took a brain break. Okay, so here we're going to mess with this whole idea of arcade games to play. So at Pluto's Playhouse, there are several different arcade games to play. Each game requires a token, and each player can earn tickets. At the end, tickets can be traded in for prizes. In my day, this was called Dave & Buster's. I don't even know if they still have those places. Hayden and Bianca play several different rounds in the machine below. Help them determine the pattern in which the machines are giving them tickets. Guys, this is what today's lesson is all about, is determining the pattern. Okay, so what pattern did I notice? Number 1. Well, I put in 3 coins, I get out 12 tickets. So I'm noticing I can have 2 different things here. I could have y equals 4 times x, or I could have y equals x plus 9. Both of those would work here. So let's go on to the next one and see which of these we can eliminate. So I put in a 5 and I get out a 20. So that's not going to work because if I put in a 5 and add 9, I would get out a 14. So this is not my function. My function is y equals 4 plus x, which is a multiplicative, 4 times x, which is a multiplicative relationship. Okay, and I could even make an x, y input-output table. Put in a 3. Put this up here again. Output a 12. Put in a 5. Output a 20. Put in a 2. Output an 8. Put in a 9. Output a 36. Put in a 6. Output a 24. So that's an XY table. And guys, if you had to graph this, that would be your ordered pair. 3, 12. 1, 2, 3, 3, and let's just say 12 is all the way up here. I would go 3, 12. Okay, so how many tickets would 8 coins produce? So what they want us to do is have 8 as our x value. So if I put an 8 in for right here, 4 times 8 would give me 32. Okay? So if these two kids play and they get 48 tickets, so this case it gives me my Y value, and I need to figure out what my X value is. How many coins did they play? So if I get 48, 48 equals 4x. Ooh, this is exciting, guys. Look what's going to happen. 48 equals 4x. What's happening to my x? It's being multiplied by 4. What's the opposite of multiplying by 4? Dividing by 4. So x equals 12. So they put in 12 coins and they got out 48 tickets. Okay. Which equation could be used to represent how many tickets T were given when coins are placed in the machine? We already figured that out. That is y equals 4x. And last but not least, what type of relationship is the equation? Is it additive or multiplicative? We know it's multiplicative. Okay, so this is just kind of the gist of it. Hold on one more second. I'm going to bring in one more thing. All right, for these, it just wants us to first decide. These are 4 different input-output tables, 4 different situations. Determine, didn't mean to do that, if it's multiplicative or additive. So, and then for extra fun, we can even find the function or the equation. So what's going on here? 2 plus 14 would be 16. So plus 14 is an option. But 4 plus 14 is 18, not 32. So I'm going to guess this is multiplicative. And what would my function be? It would be y equals 8x. Because I put in a 2, gets multiplied by an 8, I shoot out a 16. Okay, next one. What's going on here? So this could be a 4 times 2 is 8, but 6 times 2 is 12. So that's not times 2. So I'm going to say this is additive. And this is going to be y equals x plus 4. And I had to go to the next ordered pair to see that because 6 plus 4 is 10. Okay, up here, oh, we are going down. So I could say, what weird decimal do I multiply 3 by to get 2? Or I could say maybe this is additive. But it's one of those where I am adding a negative 1. Or a negative number. So I put in a 3. 3 plus a negative 1 is 2. I put in a 6. 6 plus a negative 1 is 5. So that works for that. And then this last but not least, let's see. I'm decreasing by 2.5, but I'm decreasing by 5. Interesting. So this would be multiplicative, and this would be y equals, what's happening here? How do I get from 5 to 2.5? I multiply by 1/2. Or you could write it y equals 0.5x. They're the same thing. So that's just another example to show you that you don't always have to multiply by a number greater than 1. Okay, that's just all I wanted to cover today. Hope that helps. B-Day kids, be good.